So let's talk about activity and half-life. As you probably guessed already, nuclear activity, since it's on the quantum scale, it is governed by the laws of probability. Now, if we looked at just one specific nuclei or nucleus in a sea of billions upon billions of nuclei, we don't know when that specific nucleus will actually decay. Maybe it'll decay, in 10 seconds from now, 20 minutes, a day, 50 years, who knows? We don't actually know how to say it for one specific nucleus. However, if we look at a collection of nuclei, we can kind of say, okay, well, based on a collection of nuclei, we can say, based on the laws of probability, half should decay in this amount of time, roughly, and so on and so forth. And that's the main thing when we're doing anything with statistical analysis. It only works better with large samples. So when we're talking about all these nuclear decays, nuclear activity, half-life, we're talking about having a very large sample size in order to make those claims. So when we talk about activity or decay rate, it's basically telling us how many nuclei in that sample decay within a given amount of time. So the unit for activity is the becquerel. And the becquerel is equivalent to the units of decays per second. So it's telling you how many decays you should expect every second in that sample. What we're really interested, though, in this thing called half-life. So the half-life is going to be the time for an element for half of a sample to spontaneously transmute, or half of a sample to decay, however you want to phrase that. Now, the half-life equation, which is on your data sheet, it's written like this n equals n0 to the 1/2 n. What's not on the data sheet here is this n equals t divided by t half. So let's explain this. So first of all, n and n0 are very flexible. They can play different roles. N can represent mass, it can represent activity, it can represent chemical amount, like things in moles, although we don't generally use amount. But we can certainly use mass, like something in kilograms and milligrams. We can use activity, so 50 decays per second, something like that. So n0 is the initial amount we're dealing with, whether it's initial mass or initial activity. N is going to be the activity or the mass after some time t has elapsed. N here is to represent how many half-lives occurred. In order to calculate the number of half-lives, we take the time that's been elapsed and we divide that by the actual half-life. Most times that is going to be given. You'll also notice that I didn't put any units here. We're actually very flexible with the units in the half-life equation. As long as the units on n and n0 are the exact same, you're good. As long as the units on t and t half are the same, you're good. That's the only thing you have to watch out for. Make sure that those units are the same. Otherwise, you run into some problems. Now, in Physics 30, we are a little bit restricted. We can't ask you any half-life questions where the only way to solve it is using logarithms. We can certainly ask you to do it in the case where you can apply the guess and check, but if you actually have to use logarithms, we can't ask you to do that. I will show you how to do that in an example, but we can't expect you to do that in Physics 30. So we're just going to go through a few different examples of half-life questions. So let's see what we got going on here. So we have a Geiger counter. It can be used to detect the level of radioactivity in units of becquerels. So the becquerel is, a unit of activity. So a sample of Xenon 137 has a half-life of 12 days, and it is found to emit beta-negative particles at a rate of 240 megabecquerels. So we want to write the decay equation for Xenon 137 and determine its activity after 30 days. All right, the first part here, the decay equation. So we are told it emits beta-negative particles. This is telling us that we have beta-negative decay. So the first thing is we want to write out Xenon 137 in nuclear notation. So we have an A value of 37, and then Xenon on our periodic table is element 54. So when this undergoes beta decay, as long as we remember that we have our beta-negative particle, so we're going to have 0 for the A value because it's not a nucleon, minus 1 for our charge value, and then plus the antineutrino, we can use our conservation laws to work out the daughter element. So 0 plus something has to give me 137. Well, that something is going to be still 137, because we know the A value doesn't change in beta negative and beta positive decays. -1 plus something gives me 54. Well, that something has to be 55. So element 55, if we look on our periodic table, this is going to be cesium. So Xenon 137 is going to decay into a beta negative particle, an antineutrino, and cesium 137. So to determine the activity after 30 days, we can use the half-life equation, because activity and half-life both operate on a exponentially decaying scale. So we can use activity here. Now we're told that we have an activity rate, initial rate of 240 megabecquerels. So that is what we're going to place here. So we get this 240 megabecquerels. We're going to multiply that by half. So the number of half-lives is our time divided by our elapsed time divided by our half-life. So we want to find the activity after 30 days. So this is going to be the time, and then we're given the half-life is 12 days. So we're looking at 30 days divided by 12 days. So again, we want the units of our time to be the same, so they do cancel out. That's good. And now my units of n are going to match that of n0. If I have megabecquerels here, my final answer is also going to be in megabecquerels. So that's what I was saying when we're flexible with the units. Or sorry, that's what I mean by my comment when we're flexible with the units. There's a lot of leeway on it. Anyways, what we're going to get is we're going to get the activity is about 42.4 megabecquerels. So this sample, after 30 days, it started out with 240 million decays per second, but after 30 days, as the sample kind of started to decay, after 30 days it only has a decay rate of about 42.4 million decays per second. So we have phosphorus 32. It's a substance that, it's telling us it undergoes beta negative decay and has a half-life of 14.3 days. So we have 5 grams of the original substance. We'd like to find the amount remaining after 24.6 days. So again, we have our half-life equation. So we have this 1/2 to the n. So we are initially starting out with 5 grams. So we have our 5.0 grams here. We have our 1/2. And then the number of half-lives, our elapsed time, t, is 24.6 days. And then we want to divide that by our half-life, which we are told is 14.3 days. So the great thing with half-life questions is a lot of them tend to be plug and chug. So it makes your life a little bit easier. Alright, so we got 24.6 divided by 14.3. So at the end of this, I'm going to get that n is about 1.5 grams. So what this is saying is that after 24.6 days, we should only have 1.5 grams of the sample left if we started out with 5 grams. So the next part here, this is more of a theoretical question. So we have a radioactive isotope. It produces a standard decay curve. We want to sketch the curve representing the decay and the curve representing the daughter product as a function of time. All right, the first part of this should be pretty straightforward. So we're going to have a graph. Looks like this. So on my x-axis we're going to have time, and then on here we're going to have n. Now I'm going to label this top point here as n0. This is going to be our starting amount, and I also want to deal with half of that. Now our standard decay curve, if we're looking at our original product, it's going to be an exponential decay, so it's going to look a little something like this. So we're going to decay, and then we're going to reach that line of n equals 0. But as you know from Math 30, exponential functions will not cross this axis. It'll kind of approach as close as possible, but never cross. This is what we refer to as an asymptote. Now, what's special is at this value where our decay curve, where we have half of our original amount, this time associated with that is going to be our half-life. And that's really important. Now, let's draw the actual daughter curve to this. So the pink here is my decay curve. Let's look at my daughter curve now. So at the start, when I have a full amount when I'm starting with my initial amount of my original product, I'm not going to have any daughter product because I haven't decayed yet. Now, over time, this is going to be exponentially increasing. At the half-life, our two products should be equal. Our decay product should be equal to our daughter product. So we want something that passes through this point. And similarly, if this curve can never quite approach zero, like we can never fully get rid of our original product, that means we can never have the full amount N0 of daughter product. So for the daughter product, the line N0 is also going to represent an asymptote. So we want something that exponentially increases, passes through this point, and then treats this curve like an asymptote. So probably have something that looks a little bit like this. So this is going to be our daughter curve. So this is showing our original sample decaying as a function of time, and this is showing our decay product as a function of time. So that's more of a theory question that you could be asked on an exam. All right, let's finish up with this one last example, and then I will do the more advanced logarithm one in another video. So we have artificial radioisotopes. They're used to treat cancer. So Cobalt-59, it's bombarded with neutrons. We have Cobalt-60 produced. Cobalt-60, we're told, has a half-life of 5.27a. So A, again, it just is annum, the Latin word for year. We don't usually write YR in physics. It undergoes beta-negative decay and produces gamma radiation. So the gamma rays are used to kill cancer cells. Healthy cells also die. So Cobalt, yeah, so there's a lot of background information here. This is just to kind of provide context to what you're learning and show that it has real-world applications. So we'd like to write the decay equation for Cobalt-60, and then the container of Cobalt-60 is stored for 9 years, and it's found to have 3 milligrams of sample left. So we'd like to find the initial amount that's been stored. All right, first part of this, let's have a look. So we are told that we have a beta-negative decay, and we also have gamma decay. All right, let's deal with the beta-negative first. So we're starting out with Cobalt-60. So we're going to have 60, and then if we look on our periodic table, Cobalt is going to be element 27. So then that is going to decay into our beta-negative particle plus our antineutrino. And then if we work through our conservation rules, we should get 60 as our A number because it's not changing, and then we're going to have element 28 because we want to raise the Z value by 1. And then element 28 is going to be nickel. So Cobalt is going to decay. Cobalt-60 will decay into a beta-negative particle, an antineutrino, and nickel-60. Now we also have gamma radiation. How do we include that in here to show that there's also gamma decay? All you have to do is tack on a plus gamma at the end. So that takes care of everything. This piece here, that takes care of my beta-negative decay, and that takes care of my gamma. We can write that all on one line. There is no problem doing that at all. All right, part B. So we're still dealing with half-life, so we just have n equals n0 to the 1/2 n. This time, however, we are not interested in finding n. We're interested in finding n0. So n0 is going to be n divided by 1/2 to the exponent n. Not a hard rearrangement. Now we just have to do the work on this. So the original amount, so we're told we have 3 milligrams left, and then 1/2. So our elapsed time is 9 years, so 9 annums. And then we're told that this has a half-life of 5.27 annums. All right, lots of places that mistakes can be made. Let's be really careful with this. So let's see what we got. We're going to have 3 divided by this. So we're going to get about 9.8. And then the units of n0 and n have to be the same. So if this is in milligrams, this also has to be in milligrams. Now, the main thing we want to check for, if we've decayed over time, our original amount should be greater than what we started with. 9.8 seems pretty sensible. So we're pretty happy with that. As I said, the half-life questions you get, they're not meant to be hard. They're just meant to be on the exams, those confidence boosting questions that you can get through really quickly.